So there are some minor differences between DFS and HDFS. So that's not very important. Actually, both are kind of the same. Yeah, so now we talk about MapReduce. So mapping is again, mapping is the step where we split the data. After splitting, we do some operations like shuffling. For example, we arrange all of the similar data into a single split. In that way, when these data slices are distributed to the different machines, they process this data parallelly in the reducing step. Reducing is where the operation is actually done. And because we did the shuffling and arranged all the similar data at the same place, none of these processors which are working in parallel have to depend on the results from the other processors. So none of them have to wait for or have to depend on any manner about the results produced by the other processor, so they can work, they can all work independently. And after they have all produced their results, their generated results are aggregated, and this is the final result. MapReduce is inspired by the divide and conquer rule of mathematics. So we divide the workload, and then the different machines work in parallel to convert the data, this data processing. So the main inspiration behind MapReduce and Hadoop in general was for optimizing the search engine, because search engine was a big thing back then. So that was the main kind of anticipated workload, but later on, the focus kind of shifted to the other sorts of workload. For example, these days, machine learning is the bigger guy in the room. Machine learning workload is predominant, but MapReduce is, again, like we discussed previously, not very suitable for most ML workloads. For example, most ML workloads have to repeat the same process a million times, but MapReduce is not kind of very suitable for that sort of processing. Why? Again, because it does not use memory. Okay, so here are some of these previous predecessors. Using and Natch, not very important. Mahut, not very important. And Spark is important. Okay, so the main thing about Spark is that it uses memory. So Spark uses this RDD, resident distributed dataset, instead of MapReduce. So RDD is a replacement of MapReduce in that it uses in-memory computation, batch processing technique. That's how it is faster than MapReduce. How faster? 10 to 20 times faster. And because it uses memory, it is useful for iterative and recursive algorithms. Okay, so that's the main idea you have to get from here. That Spark uses memory, that makes it faster than MapReduce and makes it suitable for iterative and recursive algorithms. Okay, and Spark also has all of these very good, very well implemented libraries for the different sorts of application. For example, SQL, real-time, machine learning, graph, you name it, and Spark has it, that sort of thing. So Spark is a very well-developed stack which has its well-developed algorithms and procedures and all sorts of steps in computation, starting from the hardware, moving up to actual application development. Yeah, so this application library of Stack is pretty rich, and Spark's use of memory, that's a very good thing. Okay, so Flink is the next step of Spark. So this is where something called Lambda architecture is introduced, which kind of makes it possible to work on batch and streaming data at the same time. So what's batch data? Batch data is, for example, your massive data set, database. You have something stored on the storage, and you fetch data from the storage and serve the request of the application. Application always requests some data which is available in your database. Like here, application is requesting some data which is present in some database, albeit a very big database. So you have to read this database in batches and serve the application. And besides that, we have the stream processing, where input data is generated every time by the system. For example, video, it's a time dependent sort of thing. So frames are generated every second. For example, if you say you have a 30 FPS video, that means 30 frames. Each of the frame is an image within the video. So 30 images are generated per second. That makes your video. So depending on how long you ran your video, you are continuously generating new inputs to be processed by the system. So that's streaming data. So Lambda architecture makes it possible to work on both batch and streaming data at the same time within a single stack. So how does it do that? So it has its different algorithms implemented depending on whether the input is for batch processing or for stream processing. So for batch processing, there is Hadoop. Hadoop is very good for batch processing. So if the data requested by the application is a batch data, this part of the architecture serves that. And if the data is streaming data, Hadoop is not suitable for streaming data. We have Storm and Cassandra systems like that for streaming data. So when the data is streaming in nature, this part of the architecture becomes active and serves the application by using suitable libraries available in Storm and Cassandra. Okay, so that's the thing. Within the same architecture, depending on the type of data, you use different sorts of tools and platforms. That's Lambda architecture. So this Lambda architecture was introduced in Flink. Yeah. So here is some summary of chapter 1, and we are done. Okay. So I have discussed all the important things from chapter 1. So now let's move on to chapter 2. Let me share the screen for chapter 2. Okay, so the chapter 2 is about real-time data processing. So what's real-time data? We discussed in the last chapter that real-time data is like video data, the data which is generated in a time-dependent manner. For example, whenever we talk about real-time data, let's consider audio and video data. Those are very good examples of real-time data, where new data is being generated for as long as you ran the audio and video. Okay, so the real-time data actually caters to the velocity of big data. So this is a very high velocity of data. A huge amount of data is being generated within a very short span of time. That's made the data high velocity, and this makes the processing of these types of data challenging. So this stack is very important. Okay, so here, especially the first two layers there, these layers especially, where we discuss the big data platforms. So we'll be particularly looking at the platforms only in this chapter, stream and data processing platforms, the analytics and the upper stacks, layers of the stack are not discussed exactly in this chapter. So These processing platforms are the steps where the data is read from the hardware and processed. So the hardware, it can be cloud, Azure, Amazon, then it can be enterprise databases maintained by IBM or Oracle and things like that, or it can be some other source of data. So these hardwares, they store streaming and other sources of data which we call stored data, which is, low velocity data, let's say, which is stable data. For example, a big database for an organization. So that is not the sort of data which is being generated with time. So that's the high volume data. It is a huge amount of data, but it's not being generated as we move on with time. That's the idea. Whereas the streaming data, maybe it is lower volume than the stored data, but the streaming aspect of it makes it challenging because streaming means that new data is being generated with time. So for the stored data processing, Hadoop and Spark, these are the benchmarks. Hadoop is the best platform, maybe the most popular in the field, and Spark is kind of the most sophisticated one. And for the streaming processing, we have platforms like Storm, Kafka, and Flume, which we will discuss in this chapter. So there are some requirements for any system which we call a real-time system. So these requirements, look at these requirements. This is important. For example, low latency. So because you have to because this data is being generated in a very fast speed, that means you have to process the data that faster, or otherwise what will happen? If you take a long time to process data, then you will lose a huge amount of data if you can't keep up with the pace. So you have to keep up with the pace. So that's why you have to do faster processing, and that's a requirement of a real-time system. Faster processing is lower latency. So then another requirement is high availability. So because your data is being generated continuously in a continuous fashion, so your system must always be there to serve the data. Okay, the data is continuous, so the system must also be continuous, and that is the requirement of high availability. So then we have requirement of horizontal scalability. Okay, so scalability means that you have to have the capacity to add or remove resources as needed. So because this is a high velocity data, streaming data is high velocity data, that means a huge amount of data is being generated within a short amount of time. So whenever that velocity changes a little bit, you have to keep up with that change in speed in real time. That means when the speed increases a little bit, you have to have resources, and when maybe the amount of data reduces a little bit, then you have to remove some resources. So all of that have to be maintained by the system. So it should be scalable. That means you can add or remove resources as per the requirement of the data. This is not something like stable fixed data. So you can just assign a particular amount of resources and you are done. It's not like that, because this is continuous data. We have to continuously keep pace with the data. Okay, so here are some boring definitions. You don't need that. Okay. Yeah, in some definitions. Yeah, here, this is important. Okay. So this shows a stack of the different tools which are used in each state. For example, in when the input data is consumed, then Flume and Kafka systems like that remain active. Their task is to consume the data. They're mainly involved with data consumption. And then the next step is saving the data to the storage. So here the storage is important. So we have HDFS storage for that. Then in the upper stack of things, we have the processing tools. For example, in case of Hadoop, we have MapReduce. In case of Spark, we have all these Spark libraries for doing the things. Then we have some platform which is specially designed for real-time processing, Storm. So all of these tools are active at this layer when the computation on the data is done. So here we have an important thing called Zookeeper. Yeah. So Zookeeper is some sort of gatekeeping sort of thing. So it kind of maintains the coordination between all of these different tools that are working. So it's kind of a lock mechanism, the kind of lock we studied in the operating system. For example, in case of operating system, we lock the files. When multiple applications want to access a single file, that cannot be allowed. So when one application opens the file, that file becomes locked and it is not available to the other applications until it is closed at first by the first application. So that kind of thing is maintained by Zookeeper. So here there's a comparison between MapReduce and RDT. Again, the main difference is the use of memory. So in case of MapReduce, you have to write everything to the storage. There's no memory involved. So you can temporarily write your inputs, write your outputs to the memory. Then you can read those intermediate results on the memory, process them again, and you keep using the memory until you reach the last step where the final computations are done, and then the final outputs are saved on the storage. So memory is storage is involved only when you first read the data and finally save the data. At almost all admins run RDT a lot faster than MapReduce. Storm and Kafka and Flume, these are important. So what's Storm? So in case of Storm, there are some terminologies like the data is consumed by the spout. So spout is something which acts like a tap. So the pipe in the tap, it has this huge amount of water, but when we open the tap, that water comes out at a fixed speed, at a continuous fixed speed. It kind of makes the speed of the data sort of stable and manageable by the system. For example, if tap didn't operate like that, what would happen? Huge amount of data would come out of this pipe and flood our house. That doesn't happen because tap maintains that. Tap has all of this data as input, but it maintains the speed of the data so that it becomes manageable for processing. So Bolt takes the stable, manageable data from spout as input and does the processing. And this whole network of spout and bolt, that's called a topology. So these definitions are important. Spout is the source of data, which kind of adjusts the speed of input data for processing. Bolt is the processing platform, and then topology is the network of spouts and bolts. So the different sources of data, they send the data to the different computation resources. This network of input and processing, that's called a topology. And this whole wrapper, this is provided to the application developers as some sort of high-level abstract functions. So those are called Trident. Trident is functions which are available to the developer for developing applications on the top of Storm by using Storm. So Kafka is some sort of tool which partitions the data according to the different topics. So it maintains the different types of data as the different topics. So, and the different applications based on the topics in which we are interested. So we can think that as these kind of applications have subscribed to the different topics they're interested in, and kind of takes or consumes data only from the topic they are being interested in. For example, if some application has subscribed to topic 1 only, then it will not take input from topic 2 and 3. It will take the input from topic 1 only. Likewise. So what's the benefit of that? The benefit is that if the application does not require some data, it does not need to be overwhelmed by those data. That's the basic principle. So that's why the data is being split into the different topics or the different partitions, and partition wise the different applications can consume the data. And Flume is kind of a channel to pass data from one part of the system to the another. For example, web server can be a source of data. So the data generated by the web server are sent by some channel to the storage HDFS. So Flume is that platform which maintains channels like that. Yeah. So just get an idea about the basic things of this system, a basic idea about how this system works. So that's important. Please don't use this lecture as your resource when you prepare for the exam. Don't rely on this lecture only. So here I discuss which topics are important and but at least follow the slides, okay? And while you are preparing, then put focus on the stuff I discussed in this lecture. But read and understand the things from the slide. Okay, so this is our first lecture on chapter 1 and 2. I will upload this lecture in Drive and share the link, and in that way, that sort of unfortunate thing will not happen when someone just view and delete the video. That was unexpected. Any question from this lecture?
No, but this is only part 1, so the other lectures won't be.
The other will be on the deep learning. So I can discuss some of the stuff here, and then I will upload the lecture also.
Okay.
Yeah.
In the exam, do you need to write any like real-time examples regarding real-time analytics?
You don't need to write anything. So it will be all, multiple choice and true false sort of questions. All options will be provided to you. Yeah. So
Is it going to be the normal browser, Chrome browser, we're going to use that?
yeah. You will normally access the Canvas. So the quiz will be published in the Canvas. It will have a fixed time span for attending the quiz. So yeah, you will fill up the quiz and submit. Okay. And like I said, I will try to book some room maybe in the library where power outlets are more available. And if I can't do that, it will be within this class. And if I can do that, I will post an announcement. Okay. So about the deep learning. So don't go too much into the theory aspect of deep learning when you prepare for the exam. That's not very important for our course.
So my question is like, what are the important stuff? Like we don't need to go. These are the theory part, right?
All of these not theory. So I will discuss. Let me see. For example, this. Okay. So what's the basic we get out of it? That in deep learning model we have some weights which kind of are the parameters which changes our input x to some output. So we have weights and biases which converts the input x to some output, and these weights and biases, these are the parameters of our system. So this is a linear function.
Yes.
Yes, we can have matrices of weights, vectors of weights, but at the end of the day, the function form is linear. So what does that mean? That deep learning is solely linear?
No.
No.
Because of this formulation?
No.
No. So what makes it non-linear? What makes deep learning work on non-linear functions?
When there is a power of degree.
We use an activation function to turn the linears
Very
into
good.
nice little
Yeah,
circles
that's the answer.
or whatnot.
Activation function is what converts these computation into a non-linear fashion. So, what's activation function? Yeah. ReLU and the softmax, these are the popular activation functions. For example, ReLU, softmax. Softmax converts the output values from the final layer into some sort of probability distribution. So the activation functions do that. You use the weights and the biases to generate the outputs, and then the outputs are converted to a nonlinear function with the use of activation functions you use in every layer. So the activation functions are there in every layer of the network to convert the values into a nonlinear domain. So besides activation function, in the network we have the loss function. So the loss function is used for training the parameters of the network. We want to know the values of the parameters W and B, which can generate our expected output. So how do we learn the values of the parameters? That function is the loss function. Okay, so that's the basic. You start with some initial random values of parameters. Then you use the loss function to train the model to learn the appropriate values of the parameters. And then within the network, you use the activation functions to convert the generated linear outputs to some non-linear function. That's how the network works. Yeah, so this is what's the goal of our network. So we want to reach some, this is our final values of the parameters, which can give us our expected output. And we start with some initial values of the parameters. Let's say we have two parameters here, theta 1 and theta 2. So that's the goal of the training. We want to reach from this state to this state. So how do we reach from there to there? So we have multiple algorithms for that. So it all depends on how many training samples we use per training epoch. So in the original gradient descent algorithm, all of the training samples were used in each step of training, all of them at once. In case of stochastic gradient descent, we use one single training sample each time, just one sample. And in case of mini batch gradient descent, we use mini batches. For example, if you have 5,000 samples, let's say we use batches of 100 samples each time. So during each training epoch, 100 samples are randomly chosen out of the 5,000 and used for training. So how many epochs we will have? 5,000 by 100, that many epochs. And in case of gradient descent, that's just one epoch. And in case of stochastic gradient descent, that's 5,000 epochs for the 5,000 samples. Okay? Yeah, so that's another important thing is overfitting. Overfitting is unavoidable. So you have to find some sweet spot that you don't fit to your training samples exactly. You do some fitting, but that fitting need to be general enough to fit some samples which are not exactly coming from the training distribution. So we don't want to learn the training distribution exactly. We don't want to memorize the training distribution because that distribution is a bit relaxed. some of the samples which we have in real life might have a little shifting from that given distribution. So we want to make it general enough so that our model can work on the, a little bit shifted data also. So that's a very difficult thing to do. So in one way, you want to learn the distribution, but you also don't want to memorize the distribution. Yeah. So as you proceed training, your training loss always decreases because you are learning the training distribution better at each step. But at some point, you start just memorizing the distribution. So this is the point where you are supposed to stop. After this point, you see that your training loss is decreasing because you have started to memorize the distribution. But the validation loss increases. Why? Because after that point, your learning loses its generality. Okay, so this is general versus specific, that trade-off. So with training, your model becomes more specific to the training distribution, but you want some generality to the model also. So this is the spot where that trade-off is satisfied. You are specific enough and general enough, but you have to find this point, this optimal training point. So with some algorithms and things like that, you can control the overfitting, but you cannot exactly solve overfitting. That's mathematically unsolvable. So what are the techniques to reduce overfitting? So these are some examples of activation functions. One popular technique for controlling overfitting is dropout. So in case of dropout, instead of training all neurons at each training step, you remove some of the neurons at each step. You randomly remove some of the neurons. So that does not mean that these neurons are exactly deleted in the system. They are trained in some other step. So in this particular step, you train these 2 neurons. At some other step, you train some other sets of neurons. So like that, at the end of all of the training steps, you have trained all of the neurons. But in a single step, you don't train all of them at once. So how does that help to control overfitting? Overfitting stems from the fact that you have too many parameters to train. That's actually the crux of the problem compared to the number of training samples. So we gave the analogy. For example, some student is preparing for the exam. So he has too few contents and he has such a large amount of time. So then what will happen? He will just start, memorizing and repeating all the small stuff, little stuff he has got. So that's it. To control that thing, you reduce the amount of time they study. So that's the same thing here. You reduce the amount of stuff they train on in each step because you have too many stuff to train based on too few data. So you remove some of the stuffs to be trained, and that's how you control the overfitting. Batch normalization is another technique for overfitting, so you can ignore that for now. Another important parameter is learning rate. It controls the speed in which you learn. Okay, so that speed is adjustable, but this learning rate is not something trainable. You don't train the learning rate. It's not your model parameter. You give the learning rate as an input to the model yourself. Okay, so you have to adjust those values yourself. It's not something the model can train itself on. So the model weights and the biases, those things the model trains itself at each step. But the learning rate is not something that the model trains itself on. Okay. So that's about the basics of the network. So then we have discussed something on CNN. So Why we needed CNN? Because the feed-forward network we discussed just now, that kind of is not suitable for classifying images due to several reasons. For example, in case of the classic network, the feed-forward network, image is a matrix, but a feed-forward network cannot take a matrix as input. Matrix like this, it cannot be provided as input to the network. So what we have to do is, we have to convert this matrix into a flattened vector. You just flatten everything into a single vector and you provide that vector as input to the model. So that creates some problems. What are the problems? You don't learn the individual patterns within the image anymore. You just consider everything at once. So if for example, your image is just shifted a little bit also, this distribution becomes a whole lot different. And the model, it will not be able to infer on distributions like this, whereas it is actually the same image, just being shifted. So when you convert this image to a vector, you can't tell how the image changed. You can't tell that it's just a shifted image. It will be a whole new image to the system, and the system won't be able to work on that. So that's the problem. Then another thing is that if you increase the size of the image, your network size increases massively. You know, it's a matrix. So when the scale dimensions of this matrix even changes a little bit, the size of the flattened vector, it changes hugely. So in that way, your network also has to become huge. So overfitting becomes very severe. So that's how we see that the feed-forward network is not suitable for image classification. Rather, we use some other concept for classifying images, which is that we learn some local patterns. For example, if we try to learn the digit 4, what do we notice? We notice that there is this horizontal sticks-like thing and horizontal sticks and the vertical stick-like things connected together to make the 4. One vertical, one horizontal, and followed by one other long vertical. So we can use the different networks to learn these individual patterns, and then we aggregate the learned patterns to learn the bigger shapes. For example, here we learn the smaller shapes, then we combine the outputs to learn the bigger shapes there, and finally we aggregate all of those features and get the final output. So that's the concept. In the lower layers or the shallower layers of the network, we learn simpler patterns, more simple patterns. And as we go deeper within the network, we learn more complex patterns within the image by combining those simple patterns. So we learn the high-level features within the deeper layers, and we learn the low-level simple features in the shallower layers. And finally, in the output layer, we learn the whole pattern of the thing by combining all of the features. Yes, these are the basics. Okay, so those different shapes, the pattern learning, that's called a convolution operation. Those are the convolution layers where we learn the patterns. So aside from that, we have some other layers within the CNN network also. For example, pooling. So what's pooling? Pooling is where we get some important summarized information out of the learned patterns. We learn the patterns in this layer, and then we summarize the output from this layer in the pooling step. So the pooling is not something we train on. Pooling is just a way to get a summary, for example, maximum, minimum, or average operation. So we don't learn this operation. We don't need to learn this operation. So this is not part of the training, but learning the patterns, the convolution step, that's part of the training. So after we do all this convolution and pooling, we finally aggregate all of the features by doing just a flattened step. So we combine all of these feature outputs within a single vector, and then we classify on that vector. So because it becomes a vector, that classification is done with the fully connected networks. So we have a series of fully connected layers at the end, which does the job of classification on the learned features. Okay, at first we learn the features by doing some series of steps of learning the patterns, summarizing the patterns, and then we combine all of the patterns into a vector and we do the classification on that vector. Yeah, that's it. And another important concept is that whenever the image has multiple channels of input, so when do we have multiple channels of input? In case of RGB image, we have three color channels, R, G, and B. So whenever we have inputs like that, the filters we learn, the patterns we learn, that also become multidimensional. Your each learned pattern, it has to correspond to one of the input channels. So when your input is has multiple dimension, your filters also need to have the multiple dimensions. That's it. So instead of a single matrix, when you have multiple channels with multiple matrices and input, then your learned features is not also just one matrix, it's also a series of matrices. Okay. Any question? Okay. So, then we have the distributed deep learning. You don't need to learn that much. This is a very simple concept. Just get a basic of data versus model parallelism. So in case of data parallelism, we partition the data. We split the data set, and each of the split is sent to a different worker, a different machine. And this machine trains the whole network on that single split. Whereas in case of model partitioning, each machine takes the whole data set as input, but parts of the model to train. So we split the model here, but we split the data here, okay? So we divide the workload by either splitting the data or splitting the model. So that's data versus model parallelism. Okay, so any question? Okay, good. Then we can wrap up for today. So all the topics I discussed today, those are important for the exam, and I will try to upload the recorded lecture also in planning. Okay, by today, and I will make the recorded lecture one available also. And please, whatever you do, like I said, don't delete the lecture or change some stuff written by other people on the Google Sheets. That's very important.
So you're going to upload in the Google?
I will upload the lecture by uploading it to Drive, because looks like somebody deleted the lecture from the sources I gave.
Yeah, I was not able to access it.
Yeah, so some people, I saw that some people viewed the lecture and then deleted it from Zoom. So I have to recover it.
Can I make an announcement?
Yeah, sure.
Good afternoon, everyone. I'm standing for Vice President for Student Government Association, and my main motto is, if you have any concerns or issues regarding anything on the campus, we have the power to resolve that. It could be anything regarding study halls, the student union, the swimming center, the dining hall, the food pantry, or anything. We can resolve that for you. And the voting started already. I would like you guys to vote for me. My name is Mohammed Zubaidi, and I'm standing for Vice Presidential role.